Hi, this is Rohan from educator.ai. Let's dive in. Let's talk about one of the quietest but most essential tricks inside a transformer, positional encoding. It's the mechanism that lets a model know not just which words appear, but in what order. And as we'll see, without it, language falls apart. Here's a concrete puzzle. The phrases, dog bites man and man bites dog, use the exact same three words. Yet one is a normal Tuesday and the other is front page news. The only difference is order. So any model that understands language must somehow feel that difference. The core engine of a transformer is attention. Each word looks at all the other words to gather context. But here's the surprise. Attention treats the input as an unordered bag. Shuffle the words and it computes the very same relationships. On its own, attention literally cannot tell dog bites man from Marali, man bites dog. Think of it like a dinner party. Attention knows exactly which guests are in the room and how they relate to each other, but it has no seating chart. Positional encoding is the moment we hand every guest a numbered place card, so first and third finally mean something. Let's build the fix step by step. First, the sentence is split into tokens, chunks of text, and each token becomes an integer ID. So far, this is just a list of numbers, and crucially, nothing here records their position. Next, each token ID is looked up in a big table and turned into an embedding. A vector, a list of numbers, that captures the token's meaning. The word dog always maps to the same vector, no matter where it sits in the sentence. That sameness is exactly the problem. Position is still missing. Here's the classic idea. We create a second vector that depends only on the slot, position 0, position 1, position 2, and we add it to the meaning vector. Now dog at position 0 is a slightly different vector than dog at position 2. The place card is baked right into the numbers attention sees. Picture the vectors as points in space. The two dog points still sit close together because it's the same word, but position nudges them apart just enough. Attention can now use that nudge to tell who came first. Order has quietly entered the geometry. But what do these position vectors actually contain? The original transformer used sine and cosine waves at many different frequencies. Each position gets a unique fingerprint of wave values like a smooth binary clock. Because waves have structure, the model can learn relationships like 2 apart or right before. Most modern models like Llama and many others use something cleverer called rotary position encoding or rope. Instead of adding a position vector, rope rotates each token's vector by an angle that grows with its position. It's a small twist, literally, but a powerful one. Here's the magic of rotating. When attention compares two words, it effectively measures the angle between their vectors. If position 1 is turned by theta and position 2 by 2 theta, the gap between them is theta, the relative distance. So rope bakes in how far apart directly, which generalizes beautifully to long sentences. Zooming out, here's where it all fits. Right after the tokens become embeddings, position is injected, either added as a vector or applied as a rotation inside attention with rope. Every attention layer after that gets to reason about order. Position is not an afterthought, it's part of the input. Let's confirm it with code. We build sine-cosine position vectors and add them to word embeddings. Watch. Dog at position 0 and dog at position 2 come out as different vectors, even though the word is identical. That difference is exactly the order signal attention needs. One more check. If we compare position vectors with the dot product, a similarity score, nearby positions score higher than distant ones. Position 0 looks more like position 1 than like position 5. The encoding carries a real sense of distance, which is precisely what order-aware reasoning depends on. A few traps to avoid. Positional encoding is not a plain counter tagged on the side. It's blended into the same vectors that carry meaning. And modern rope doesn't add a position vector at all. It rotates the existing one inside attention. Mixing these mental models up leads to a lot of confusion. Here's a quick review lens. On the left, the healthy picture. Position enters early, fuses with meaning, and rope captures relative distance. On the right, the traps, expecting bare attention to grasp order, treating position as an afterthought, or pushing a model past the sequence length it was trained on, where positional patterns break down. So the big picture, attention on its own is order blind. It sees a bag of words. Positional encoding fixes that by fusing position into the token vectors, and modern models rotate those vectors with rope to capture relative distance. That single idea is why a transformer can tell that dog bites man and man bites dog are two very different stories.